The answer for the question is B. As you can see that for line 2 and line 1, if I were to draw a little tangent for line 2 and draw a little tangent for line 1 when time is 0, the slope of the tangent for line 2 is much steeper than the slope of the tangent of line 1. That means my line 2 has a faster reaction rate. That's the first one. The second one is the mass loss of line 2 is more than the mass loss of line 1. Both of these lines represent the weight loss of my magnesium. That means when I have a bigger changes in the mass of my magnesium, then I'm actually producing more final product as well. The quick reaction for that is magnesium plus hydrochloric acid yields hydrogen plus magnesium chloride. If I have more accurate instrument to measure time, that would not contribute much change for my rate of reaction. That would probably make my slope a little smoother if I have different data points. So that's not a correct one. For answer number C, the same mass of magnesium in smaller pieces, that only changes the rate of reaction but does not change the amount of product. Lower temperature is the same thing. Only the second one, the same volume of a more concentrated solution of hydrochloric acid. If I take a look at the reaction in N equals concentration times volume, if my concentration has been increased and the volume stays the same, then my initial amount of my reactant will be more, and that means I will in the end produces more product. So more hydrochloric acid for my initial amount, in the end will produces more hydrochloric acid compared to the other ones as well. Now we're going to talk about something called Maxwell Botzman distribution curve. What is Maxwell Botzman energy distribution curve? How does catalyst changes the energy distribution curve, and how does temperature changes it? The first one, what is Maxwell Botzman distribution curve? Well, here's what does it look like. So it is a graph that describes the distribution of energy of gas particles. So imagine you have a beaker of gas, okay, or a balloon of gas. If you use a super magnifying glasses and take a look at it, actually all of your gas particles are moving around at different speed as well. The ones that are moving around at a higher speed will have a higher kinetic energy. The one that are moving around at a lower speed will have a lower kinetic energy as well. Now we start to count off all the particles that have the same energy at certain points. So let's say for how many particles do I have that has kinetic energy that's 1 kilojoules? And I count out, oh, there's actually 5. So that's why my 1 data point. And then I count out how many particles that I have at 2 kilojoules, and I find out, oh my gosh, there's actually, if I count it out, there's 20 of them that has the same energy as being 2 kilojoules as well. So on and so forth. In the end, we're going to plot a graph basically that describes the distribution of energy of gas particles, especially your x-axis will be energy and your y-axis will be number of molecules. So there'll be different number of molecules at different that has different energy point. And the energy comes from the kinetic energy because they're all moving around. Okay, one interesting fact is that do you know all the nitrogen gas in the air, which consists of 80%, 78% of the air, all of them at room temperature is actually moving at a speed at around 1800 kilometers per hour. And Shinkansen in Japan actually moves at around a speed of 300 kilometers per hour. So all those nitrogen particles at room temperature, which is 20 degrees Celsius, is actually hitting us with a speed that is so much faster than the Shinkansen, which is quite fascinating, I think. Now, what is Maxwell Botzman distribution? And basically there's two people, Maxwell and Botzman. They come up with the same idea at the same time, so we give them both credit for the Maxwell Botzman distribution curve. Their hypothesis is energy is distributed statistically over all of the available particles. So different particles will have different energy points. As you can see that in your Maxwell Botzman distribution curve, actually this is a better one, there's several features to notice. The first one is your Maxwell Botzman distribution curve is not symmetrical, meaning that this is a symmetrical regular graph, and this is a non-symmetrical regular graph. It is non-symmetrical, and there are fewer particles at a lower energy point, and there's a fewer particles at the higher energy point as well. The majority, or the biggest number of the particles or the molecules is actually in the middle range over here as well, which makes sense. So most of the particles are somewhere in the middle range, and there's less amount of particles in the higher range and less amount in the lower range as well. The second part is, as you can notice that your Maxwell Botzman distribution curve is starting at 0, 0 point. 0, 0 data point. That means when the energy is 0, there's actually 0 particles that possess that 0 energy. That means there's no molecules that have 0 kinetic energy. In another way, that all particles are moving around. Okay, the next one is, at a higher energy, the line does not really reach the energy axis. So the energy axis, which is a x-axis, at a higher energy point, you don't really draw it of meeting the line, which is incorrect. We always draw it at a little bit above the energy axis. The reason for that is we found out at almost any energy except 0 kinetic energy, especially at the higher energy, you will always have a few molecules that actually possess a high energy. So let's hypothesize at infinite energy, there's still going to be some molecules that possess that energy point, which is quite interesting as well. The next part is, the area under the curve represents the total number of particles and will not change at all. So in a system the beaker system, as long as it's a closed system, if I put a top on my beaker or a balloon that I close the mouth of my balloon, there's always going to be the same amount of gas particle. If I change the temperature, if I increase the pressure, or if I squeeze my balloon, the number of particles does not change. And the number of particles has been represented by these areas, the whole areas underneath the curve, that will not be changed at all in any given circumstances, as long as a closed system. Now let's take a few examples. So how does the effect of temperature changes the Maxwell Botzman distribution curve? Well, how does temperature changes a gas particle? Now we know that when we give the gas particle higher temperature, it will possess a higher kinetic energy, much more than before. Some of them will be moving so much faster, which will be higher kinetic energy. When we plot the graph of Maxwell Botzman distribution curve under different temperature, you will see that, and this curve is actually a little bit incorrect because all of the line cannot meet the x-axis. When your temperature is increasing, your graph is getting broader and flatter as well. And here's one example, getting broader and flatter. The reason for that is you're always having few particles with a low energy, and you have more particles with a high energy, but the majority of the particles is shifting and to have a higher kinetic energy. Remember, you have the same amount of particles in your system. You're not changing the number of particles in your system. To not change the area of this whole graph, we have to somewhat shift this graph and make it go flatter and broader to make sure they have the same areas underneath. That's why your graph is getting broader and flatter. And because the majority of your particles has been possessed a higher temperature range. So there will be more particles have more energy than activation energy. So let's say if for this graph, we will have activation energy. For 300 K, 300 Kelvin. The proportion of the particles that have the enough energy or more than activation energy will be represented by this. And the particles that afterwards who has more energy than activation energy, basically in 310 kelvins, the particles that has more energy than activation energy will be represented by the green area. So as you can see that there will be more particles have more energy than activation energy, as you can see an increase of this area, and that means you will have a greater proportion of successful collision, meaning that more particles will be able to collide with each other and perform your reaction. So that's temperature. And in other words, your rate of reaction will increase. We will also have something called catalyst to change the rate of reaction, and also that will change the Maxwell Botzman distribution curve as well. Now we know that catalyst, it will lower the activation energy, and in another way, more particles will have enough energy to react. What does it look like? Well, it looks like basically from in here. When we have no catalyst, this is the energy point that has no catalyst. Only the particles that have higher energy than this energy point are able to react. Now, when we add on the catalyst, it actually lowers activation energy. So it's shifting this bar of activation energy into a new one, into the right place. And as you can see that there will be a greater number of particles that has more energy than activation energy. That means they are able to do your reaction as well. So here's another graph that explains the same thing. As you can see that the green line or the green area has been represented of all of the particles that has more energy than original activation energy. When we add the catalyst, you will have a new activation energy because it will kind of changes or shift this activation energy bar. There will be more particles that actually have more energy than the new activation energy. So all of this area will be all the particles that are able to react right now. Okay, here's our learning check. Make sure you sketch two Maxwell Botzman energy distribution curve on the same axis and y-axis for the same sample of gas, one at a temperature of T and one at a higher temperature. So you gotta label both axes and also explain why raising the temperature increases the rate of a chemical reaction. Make sure this question is worth 4 points. Okay, now let's take a look at the graph. Here's 2 points being donated to your graph. So make sure you correctly label axis showing number of particles for your y-axis and your kinetic energy for your x-axis. If you say energy, that will be fine as well. So 1 point. The second point will be denoted for the shape of your graph. So make sure your graph T temperature, your curve must not touch or cross a axis, and also the curve has to be to the right of T with the peak lower than T. So the new T has to be to the right of your older T initial temperature, and the peak has to be lower than the other one. Here's parts that will be denoted to your explanation. Okay, there's 2 things you need to mention. The first one, what happens when you increase the temperature? So when you increase the temperature, that will increase the kinetic energy of the particles, or you can say more particles will have enough activation energy. And also make sure you're talking about there will be more collisions per unit time, or the frequency of collisions, or there's more successful collisions. Make sure you're always talking about frequencies or per unit time, because we're talking about rate of reaction, so it's always a matter of time. So to get full points, make sure you're always talking about time and frequency as well.